Hello and good afternoon, everybody. My name is Jeroen Hoosemans and I will be one of the hosts of today for this TN2 meeting. And my co-host today will be Rob de Bie. And Rob de Bie is a neurologist and also the team leader of the Neurodegeneration program of the Amsterdam Neuroscience. And Rob will also introduce you later today to this neurodegeneration team. But before we start off, I will give you some quick instructions for this webinar. I think the most important instruction is that you will only see the presenter during this meeting. And there's an option for you to raise questions, but therefore you have to use the Q&A box in the bottom of the Zoom webinar. And after the presentations, we will select the questions and ask them directly to the presenter. Another nice feature of the Zoom is that you can look at both the presentation and the presenter. And if you use the middle bar and shift it around from left to right, then you can even increase either the presentation or the presenter, so you can choose yourself. Small word about the TN2 conference. So TN2 stands for Translational Neuroscience Network, and we have these conferences to bring together the basic scientists, the clinicians, as well as the industrial partners. And normally we have these nice on-site meetings in Amsterdam and also in one time in the Amsterdam Arena. But with this Corona situation, we now decided to have these lunch series. And for the next half year, we will be having a lunch series around the different programs of the Amsterdam Neuroscience. So every month we will present one of the programs of the Amsterdam Neuroscience. And today we have presentations about the program Neurodegeneration. And one of the leaders of that of the Neurodegeneration is Rob de Bie. And Rob will tell you something a little bit more about the Amsterdam Neuroscience and especially the Neurodegeneration.
Thank you very much, Jeroen. Am I in now? Because I can't see myself.
Yeah, you're in.
Good morning, good afternoon, everybody. So the Neurodegeneration program is one of 5 programs at Amsterdam Neuroscience. And we cover Alzheimer's disease and Parkinsonism and Parkinson's disease. We have the clinical research units and are linked together with the basic scientists. And I think a lot of people know about the program.
Okay. And this has more information about the Neurodegeneration program. Today we have invited 2 speakers who will talk about neurodegeneration. The first speaker is Monty Silverdale, and the second speaker of our own Amsterdam neuroscience is Anouk Rijs. But first, let me introduce to you Monty Silverdale. Professor Silverdale is a consultant neurologist at the Manchester Center for Clinical Neurosciences and a professor of neurology at the University of Manchester. He jointly runs the Greater Manchester Complex Parkinson's Disease and Movement Disorders Service and is a neurology lead for the Greater Manchester Deep Brain Stimulation Program. His research interests are in developing and improved biomarkers in Parkinson's disease and understanding non-motor symptoms, and especially pain in Parkinson's disease. And he also runs a number of clinical trials in Parkinson's disease and deep brain stimulation. So, Monty, you can, I think, unmute yourself. And yes, there you are. And
hello.
Hello. And I think you can, I will stop sharing my screen and you can, I think, start presenting. So welcome, Monty.
Hi there, thanks for inviting me to speak today. I hope you can all hear me okay, just kind of tell me if you can't. I'm going to talk today about diagnosing the descent of Parkinson's with mass spectrometry and Joy. So this is a picture here of Joy Milne. Joy is a retired nurse from Edinburgh, and Joy is sitting in front of a mass spectrometer machine, smelling the chemicals as they come through and pressing a button when she thinks she can smell Parkinson's disease. So this is a somewhat crazy situation to get to. So what was Joy smelling and how did we get there? I'm going to tell you the story about that today. So we have to go back a bit. This is a picture taken in 1982, and you can see Joy in the center of the picture and her husband Les on the left side of the picture there. And Joy is what we call a super smeller. We know these people exist in the population. They have much better senses of smell than the rest of us do. They often work in the wine industry, the perfume industry, and so on. And Joy had always known that she had a really exceptional sense of smell. And it was around this time in 1982 that she noticed an unusual musky smell on her husband, Les. She said to him, have you changed your aftershave? Have you're using a different shower gel? And he's like, no, I'm not. And he gradually became a bit more irritated by these questions. And so Joy stopped asking them, but this musky smell continued. And it was 12 years later, in 1994, that Les developed some mobility symptoms and he was diagnosed with Parkinson's disease. So he'd had this musky smell through this whole 12 years before he developed any symptoms. Now we move forward a little further to 2009, and now Les is more disabled by his Parkinson's, and Joy and Les are members of Parkinson's UK, which is the main kind of Parkinson's research charity in the UK. And Joy has noted that when she's gone to Parkinson's UK meetings with Les, or when she's gone to clinics with Les, that the other people with Parkinson's that she meets, they have this same musky smell that she's noticed on Les. And so in 2012, Joy's at a Parkinson's UK meeting, and this chap here, Tulu Kanath's giving a talk. He's an expert on stem cells. And at the end of the talk, when they're asking for questions, Joy asks Tilo whether people with Parkinson's have an unusual musky smell. And Tilo says, well, I never heard of this, but to his credit, he decided to take her seriously. And what he did is he got 12 people to wear T-shirts overnight. 6 people with Parkinson's and 6 people without Parkinson's, and then took the T-shirts off, coded them all and gave them to Joy and said, okay, if you can smell Parkinson's, you tell me which of these T-shirts was worn by someone with Parkinson's and which without. So Joy got all 6 Parkinson's T-shirts correct, and she got 5 out of 6 control T-shirts correct. So 11 out of 12. There was clearly something in this, and we were quite amazed at how well she had done. But there was this one chap, and this is a chap called Ken, and he was one of the controls. He didn't have Parkinson's at the time of the study, but Joy said when she smelled his T-shirt that he did. And it turns out that 9 months later, this chap developed some mobility symptoms. He goes to see his doctor, and he contacted us to tell us that he actually had been diagnosed with Parkinson's disease. So almost too good to be true. Joy was able to diagnose him before he had any symptoms of the condition. And this is an interesting picture that Joy herself actually drew. And this is a picture of how she can smell things. So if she's walking in this room, she can almost see the different smells coming from different areas. She can almost kind of direct herself around the room just by seeing smells in different places. And interestingly, the smell wasn't coming from the armpits. We associate kind of sweaty armpits with smell, but that's not where it was coming from. It was coming from the neck and the upper back. And we think that what Joy was smelling is what's called sebum. Sebum is an oily substance that we have on our skins of our foreheads. It causes acne, for example, the skins of our upper backs. And we've known for almost 100 years that sebum is increased and altered in Parkinson's disease. And we think that this increased altered sebum is what the chemicals in that are what are causing the difference in body odor that Joy can perceive. And so it was around this time that Thilo Knath contacted Perdita Barron. Perdita is a professor of chemistry here in Manchester, and they contacted myself as well as a Parkinson's researcher. And we discussed, these T-shirt experiments with Joy, and we decided, can we actually look at this in more detail using a clinical study? Can we show, are the skin chemicals different in Parkinson's? Because Joy must be smelling something, and so there must be changes in the chemicals in Parkinson's disease compared to people without Parkinson's. And can we use this to develop a diagnostic test for Parkinson's, a simple skin swab test, for example? And can we diagnose a condition much earlier than is currently possible? Remember, Joy can perceive this smell some 12 years before her husband got any symptoms. So can we diagnose a condition much earlier? And early diagnosis is going to be crucial if we're going to improve treatments. And of course, we need funding to run this type of study. And we were lucky enough to get funding from Parkinson's UK and also from the Michael J. Fox Foundation. And so we were able to set up a research study. Initially, the study was run in 25 centres around the UK, but now we're running it across other centres in Europe, in the Netherlands, for example. But the data I'm going to present initially is from the first 64 participants. And what we did was we took skin swabs just using some gauze or using a Q-tip on the areas that you can see in the picture there on the forehead or on the upper back. And these skin swabs were simply sent in to Manchester, just posted by first-class post, but posted at room temperature. And then when they got to our lab, they were frozen and then analyzed at a later stage. And they were analyzed using a technique called metabolomics. And metabolomics, in simple terms, involves using fancy chemistry to identify all the chemicals in the swab, and then using fancy statistics to identify which chemicals are different in the different samples, for example, in Parkinson's versus controls. And the technique we used in the initial experiment that we did was a technique called thermal desorption gas chromatography mass spectrometry. So I'm going to try and explain to you a little bit about how this technique works. I'm quite kind of mindful of the fact that I normally talk to doctors and things, and I know there's a lot of scientists on this chat, and in particular, my co-speaker, who know a heck of a lot more about this than I do. But nonetheless, I'm going to try and just tell you my understanding about how this kind of analysis process works. And I think it's useful to imagine the first bit, the gas chromatography bit, as being a bit like a 100-meter race. Imagine, if you will, that you're sitting in a room and the blinds are up so you can't see outside, but there's a 100-meter race going on outside. And you can hear a bang when the race starts, and then you can hear another bang when somebody crosses the line. And you've got to decide who it was that crossed the line based on how long it took them to get there. And there's three people in this race. There's this chap here, Usain Bolt, the 100-meter world record holder. There's this chap here who looks like he's not particularly fast with his frame. And there's this chap here whose athletic days, sadly, are quite a long time behind him. So bang, the race starts, and then 9.74 seconds later, bang, the gun goes off again. And you go, I know who that was. That was Usain Bolt crossing the line. And then bang, a few seconds later, 13, 14 seconds, whatever it would be, you go, I know that was me crossing the line. And then at kind of 25 seconds, the gun goes off again. And that was almost certainly the old bloke kind of hobbling across the line with his frame. So you could tell which person it was just by how long it took them to get there. And that's the principle of thermal desorption gas chromatography. So in this schematic, what you can see on the left side is the chemicals. I don't know if you can see my cursor or not, but the chemicals in the test tube on the left side, and we heat it up so the chemicals come off the gauze swab and they go to this thermal desorption area where they all stick. Remember, we're looking for volatile chemicals here in this study because Joy can smell them. And so almost certainly they have to be able to get into the air in order to get to Joy's nose. And so we're looking at the chemicals that can come off the swab and go into the air. Now, this is a starting line of a race. And what we do is we slowly increase the temperature, and different chemicals will come off at different times, depending on how volatile they are. So in a sense, some chemicals get a head start. Then they run through this gas chromatography column, and the chemicals go through at different rates, depending on how hydrophobic or hydrophilic they are, how much they like water, how much they dislike water. That will depend on how fast they go through this whole system. So they're being separated in time, all coming through at different times, all the chemicals in the swab. They go through this mass spectrometry machine, which I'll talk about in the next slide, and then they go to our detector. And of course, they come through at different times, and we can see the chemicals coming through on the detector. And so we can tell by how long it took to come through what the chemical is. And also we can tell by the size of the peak how much of it there is. So that's how we kind of identify all the different chemicals in the swab to compare between Parkinson's and control. I also mentioned, if we go back to this diagram there, that we've got this mass spectrometry thing in the middle there. I'm just going to talk a little bit about what that is. So that is basically an incredibly accurate weighing machine. So if we take another analogy, imagine, for example, I get every person in this talk to go and stand on a set of scales, and we get your weight on my screen. And then I say, okay, I'm not going to look, but I want somebody else to stand on the scales and I'll tell you who it was. So somebody stands on the scales and I look at my computer. I'm not looking at who's on the scales. I just look at my computer and it says 70 kilograms. Well, I don't really know who that is. That probably could be a lot of you. But if it says 70.164285943.7 kilograms, if it's really, really accurate like that, well, I know exactly who it is. I know exactly. So if you weigh a chemical very accurately, you can identify exactly what it is. And that's the principle of mass spectrometry, which I've got a little schematic to show you how this works. So we've got our chemicals coming through. Remember, they've all been separated in time, different chemicals coming through at different times. And then on the left here, they go through, they get bombarded with electrons. It's a bit like snooker balls or billiard balls, and the electrons sort of bang out the electrons from the atoms. And so all the atoms become positively charged. And most of them, they lose one electron and they get one positive charge. And then they get fired through this electric field, or in some cases, a magnetic field, and they get deflected by the field. And you know, if you're using a baseball bat, for example, when someone throws a cannonball at you and you whack it, because it's so big, you're not going to be able to deflect it very far. But if someone throws a tennis ball at you and you whack it, you can deflect it really, really far. And so how far something is deflected tells you what the mass is. So the first chemical comes through, it's a big chemical. It doesn't get deflected very far. The second chemical comes through, it's a medium-sized chemical, it gets deflected a bit further. And then the third chemical comes through and it's a small chemical and it gets deflected more. And so we can tell exactly what the chemical is. We can get exactly the mass of the chemical just based on how far it's deflected. And if we know the exact mass, we can very accurately, then we can tell what the chemical is. I should add, especially as there are other chemists on this talk, that what I've presented here is quite an old-fashioned way of doing mass spectrometry. It's done slightly differently these days using a thing called a quadrupole mass spectrometer. But the basic principle is the same, that the different masses of chemicals are deflected a different amount depending on what size they are, and we can then identify exactly what they are based on their exact mass. And so this is the full thing then. You get your chemicals, they come through, they're all coming through at different times. So you're fairly confident what you are dealing with. But then you take, for example, this peak here, and you know how much of it there is. You look at the mass spectrogram of it, and it tells you exactly what the mass is. And now you know exactly what chemical you're dealing with. And then you look at hundreds of chemicals, you compare Parkinson's and control, and you can look using statistics to see which chemicals are different between these two conditions. And when we do that, we see that we can indeed identify Parkinson's based on the skin swab just by looking at the chemicals in the sebum. We saw in particular 4 chemicals, but really quite a lot of chemicals which are different between Parkinson's and control, and enabled us to diagnose pretty accurately whether people have got Parkinson's or not. And here's a schematic of the chemicals that we identified in the first set of experiments. They're all lipids. They've got long names like octadenochol and eicosane, but they're lipid chemicals which are different in the sebum between Parkinson's and control. And what we can see in this, this is a picture that I showed right at the start of the talk. And we come back to this now, and this is Joy, and she's sitting at the mass spectrometry machine, smelling the chemicals as they come through and pressing a button when she thinks she can smell Parkinson's disease. Remember, the chemicals are separated in time by the gas chromatography, so they're all coming through at different times. And there's a kind of Y port. So the chemicals, some of them go towards the mass spectrometer and the detector, and some of them go towards the nasal port that Joy is smelling from. And so she presses a button, and interestingly, she pressed the button at exactly the same time as the chemicals that we also detected to be different in Parkinson's disease. And so in a sense, we get a second validation that what Joy is smelling and what we're picking up with all this fancy chemistry is the same thing. And so we published our first paper on this a couple of years ago in this journal, ACS Central Science, which is a high-impact chemistry journal. And about a week before the paper was to be published, the journal contacted us and they said that they wanted to do a press release. They thought there might be some interest in the study, some media interest, so they wanted to do a press release. And I didn't think much of it at the time. I thought, yeah, whatever, if you want to do that, that's fine. But the press release goes out, and from my point of view, all hell broke loose. I found myself at the center, we all found ourselves at the center of a media storm. There was a heck of a lot of media interest in our study. This is a metric that the journals use called the Altmetrics attention score. And the journal contacted us a week or so after the paper had been published to tell us about this. This metric basically looks at how much media interest there is in different papers. It looks at the standard media like radio, television, newspapers, and it also looks at the modern media like Facebook, Twitter, Instagram, Reddit, and so on. And it combines it all together to get a number. And the number for our paper was 1133, which is the highest score this journal ever had. It was a high impact chemistry journal. There'd never been more than 1,000 before. So there was just immense media interest in the study at the time. And for me, this culminated in an appearance on the BBC Breakfast Sofa. The BBC Breakfast is the kind of main UK television programme. It's watched by an audience of several million. And I got to kind of sit on the sofa there. You can see me with Joy Milne, the super smeller, and the two presenters. And this is easily the scariest thing I've ever done in my life. I think it's something that's nice to do once, but I'm certainly never going through the stress of sitting live on that sofa again. But it was a good experience to get to sit there. So what about next for us? I've talked about some data that we presented a little while back. Obviously, things have become a bit stalled because of COVID, but we are kind of getting back up and running again. We now have actually over 2,000 participants who we have skin swabs from in our study. And one thing that we really want to do is look much earlier in Parkinson's disease. We know that the neurodegenerative process in Parkinson's starts a long time, maybe 15, maybe 20 years before people develop mobility symptoms. They don't actually develop mobility symptoms and reach a diagnosis until what's called stage 3/4 Parkinson's disease. And there is their prodromal phase beforehand, before they get this clinical Parkinson's. And if we look at the nerve cells in the brain, for example, the dopamine neurons in the substantia nigra, we see that they are degenerating all right from the start. But the clinical symptoms kind of come on gradually. And it's only here where a diagnosis is made. And by that time, perhaps 60 or 70% of the dopamine neurons have already degenerated. What we really want to do is use our skin swab test to enable a much earlier diagnosis of Parkinson's. Remember, Joy can smell this musky smell some 12 years before Les gets the condition. And we think this will really improve our chances of better treatments, maybe even a cure for the disease. If you imagine, for example, trying to cure cancer when it spreads 70% around the body, it's going to be very difficult. But if you can catch it 10, 20% stage, then a cure becomes much easier, much more realistic. And we hope with our skin swab test, it will help us to achieve this. People with prodromal Parkinson's, even though they don't have kind of mobility issues, there are some clues. They can have symptoms such as a loss of sense of smell. They can have certain sleep problems, constipation, depression. Of course, these are quite common symptoms in people as they get older anyway. Most people, when they lose a sense of smell, it's nothing to do with Parkinson's. But if we have this cohort of people with these symptoms, it gives us people to target with a skin swab and try and enable a much earlier diagnosis and show who is actually in the early stages of the disease. Another interesting study that we published earlier on this year was using a slightly different technique, this time liquid chromatography. This is looking at all of the chemicals in the skin swab, looking at much more chemicals. Our first study I showed was just looking at the volatile chemicals, the chemicals that get into the air. Here we're looking at all the chemicals, as many as we can really in the skin swab. So we get thousands of chemicals and we compare between Parkinson's and control. And what we did was we then ran it through kind of fancy database software, which tells us which chemical pathways are altered in Parkinson's versus control. And what we see is certain pathways, including one called the carnitine shuttle, and also certain mitochondrial pathways, which are showing up as being altered in Parkinson's. And interestingly, in other people who have done experiments looking at the brain in Parkinson's, in post-mortem samples or in animal models of Parkinson's, they see exactly the same chemical pathways are deranged in the brain that we are seeing simply on a skin swab. So it's almost as if by swabbing sebum, we're getting a window into the dysregulation of mitochondrial metabolism in Parkinson's disease. When I first saw this data, I was a little skeptical. I thought, what about the blood-brain barrier? Surely that stops chemicals getting in and out of the brain, and how could you pick it up in the skin? But of course, we're looking at lipids here. We're looking at fatty chemicals, and fatty chemicals can pass through membranes, just going down concentration gradients. They don't care about the blood-brain barrier. And so it's quite realistic to understand that when we swab the skin, we're actually getting a window into what's going on in the brain. So this was, I thought, quite a fascinating finding, and we published this in Nature Communications just earlier on this year. And finally, that just leads me to this whole idea of using sebum as a diagnostic biofluid. We kind of stumbled across sebum and skin swabs as a way of diagnosing disease. We stumbled across this because of the whole story with Joy. But we now think that when people get diseases, or when they get, when there's any kind of alteration in what's going on in the body, that leads to alterations in the chemicals in the sebum, and they become trapped there for weeks and weeks and weeks, a bit like a bird being trapped in a cage. And so the chemicals in the sebum really tell you a lot about what may be going on in the body. And now that we have this technique that we've managed to kind of develop to swab sebum and use it as a diagnostic biofluid, maybe we can use it for lots of other diseases as well. And the lab now, interestingly, have got some data on tuberculosis and also on COVID. And believe it or not, we can diagnose both these conditions very accurately simply by swabbing the sebum. And funnily enough, I was speaking to Joy yesterday, and she was telling me about the smells of these conditions. For what it's worth, COVID apparently smells like green apple cider, and tuberculosis smells like wet brown cardboard. So make of that what you like. And finally, I'd just like to thank the other people involved in this study, Pridita Baran, the Professor of Chemistry at Manchester University, who's run the whole chemistry side of this, Ellie and Drupad, the postdocs who've done really most of the work for this study, all the principal investigators and the patients and participants at the 25 sites around the UK and all the other sites around the world, including the 4 sites in the Netherlands. Thank you. Stop share. Hiya.
Thank you very much. Is Jeroen coming in? It was an excellent talk, Monty.
Thanks, Rob.
Yes, I'm here. Oh, sorry, I had some technical problems, but Monty, that was an incredible story, really amazing. And yeah, I think the way you told how you discovered it and ending up in the morning show at the BBC, I think it was really great to hear. I think there are a couple of questions, but maybe Rob wants to start off with a question.
So when Monty, when you when this all became very publicly and with the publications and on the news, were there other people, other super smellers who contacted you and who were interested to be involved in projects?
Yes, yeah, there was actually quite a lot of people that contacted us and said that they also thought they could smell Parkinson's. We kind of thought about, just doing a study on people, sending them out swabs and see if we could find other people like Joy. And we haven't really got around to doing that yet, but yes, certainly a lot of people have contacted us and said, yes, they think they can smell Parkinson's as well, but we haven't tested them properly like we have done with Joy.
Okay. And I have one small other question is that, there are several causes of Parkinson's disease, genetic contributions to risk factors for Parkinson's disease. Do you know, or do you have genetic information of the whole cohort so you can see whether or not there is a difference?
At the moment, we don't. We are planning phase 2 of the study, and that's certainly something we're going to look at is the genotypes, disease stratification, there's different types of Parkinson's like tremor dominant and so on. And we certainly want to look at all the genotypes, all the stratifications of different types of disease, but we haven't done that yet. The initial study was, we wanted to make it as easy as possible for people to be included. So it was very little clinical information. They've got Parkinson's. This is a medication they're on, the date of birth, a bit about the height and weight and things, because you need that for the metabolomics, but that was it. So we wanted to keep it easy. So the collection only took 5 minutes. So there's very little, we need to do it again now with more data.
Okay.
So I also have some questions from the Q&A. One is from Micha Wilhelmus. He asks if there is a relation with the presence of alpha-synuclein in the skin, because there are also reports that alpha-synuclein in the skin. Can you directly correlate that, or correlate it with maybe disease mechanisms that you can maybe also see in the skin?
Yeah, we're very interested in whether there's any correlation with alpha-synuclein in the skin. The way they do the metabolomics, proteins like alpha-synuclein don't make it into the setup because we don't look at them, but it would be good to do that. We certainly have discussed this, and it's an intriguing link that there is alpha-synuclein in the skin, but we don't have any data on that either. As I say, the initial study, which is all we have so far, is very limited in its sort of in that type of data.
Yeah. As another question is maybe related to that is from Paul Lucas, and he asked if there's like correlation with other metabolites, especially maybe in the blood of the brain, in the microbiome, that they can be linked to what you see in sebum.
Yeah, no, we have a link with Philip Shepherdjans, who you may know. He's a Dutch chap, but he works in Finland, and he's one of the big guys for studying the microbiome in PD. And we are looking at, he's got a cohort of people that they have detailed microbiome data on, and we are looking at doing skin and blood work, metabolomics, to see if we can link all this in. We have some blood data, but I don't think we have the skin data on that yet, but that's certainly something which is in the planning.
Yeah. No. So the last question I will post from the Q&As from Arjen Brussaert, and he asks if the outcome of the mass spec of the sebum also correlates with the clinical outcome measures of Parkinson's disease, like the DAT scans or the MDS UPDRS scores.
Yeah, so like I say, the initial study we didn't have that clinical data. We had very little clinical data. We do have maybe 50 or 60 samples with more detailed UPDRS and things like that. Not DAT scans, but UPDRS that we are looking at. But we're going to plan the next study, which is going to have all the clinical data. So that's all what we hope to do next, really. But we don't have that data yet.
Okay, great. Yeah, there are a couple of questions that are not on the Q&A, but in the chat. But also because of time, I propose that we forward you these questions, and maybe you can answer them separately.
Yes, of course.
Or through the TN2 organization. So thank you, Monty. You will come back at the end of the session, but for now, we have to move on to the next presentation by Anouk Rijs. And Anouk Rijs is a professor, and she leads the analytics of biomolecular interactions group within the division of analytics of biomolecular interactions at the Amsterdam Institute of Molecular and Life Science at the Vrije Universiteit. And Anouk and her group are especially interested in the integration of molecular spectroscopy with mass spectrometry to understand complex biological processes at the molecular level through the characterization of molecular structure and intermolecular interactions and structural changes. And at this moment, Professor Rijs is also interested in peptide and protein aggregation related to neurodegenerative diseases, and also how this aggregation is relevant for the biological function for biopharmaceuticals and bioengineering of smart materials. And I think today Anouk also will talk about Parkinson's disease, and I also assume about maybe something about alpha-synuclein. So Anouk, I can see you. You can start sharing your screen, and welcome, of course.
Yes, thank you. Is it now shared? I don't see that. So do you see my screen?
Yes.
Okay, good. So yes, thank you very much for having me here and and this nice introduction. It's a pleasure to show our work, what we are doing at the VU in Amsterdam. And well, slightly different than Monty's talk, I would show you a bit more of the technical side, how these measurements are done. So in our group, in our department, we aim to understand and control neurodegeneration. And for that, we look both at the fundamental level and at applied, apply to, for example, indeed the Parkinson's diagnosis that Monty recently just explained us. So in this talk, I will show you a bit on what we do on studying molecular mechanism. I'll show you a flavor of how we want to control and direct the aggregation. And of course, these techniques that we are developing are also used in the diagnosis for Parkinson's. But at the heart of our work is the instrument development and then the technical development to do all this work. So to actually come back a little bit to the work that Monty just showed. So he ended with this slides showing about the many sites in the UK and then the few sites in the Netherlands. And this is in collaboration with Rob de Bie, where we could join the end of his LEAP study. And here, Perdita Barron is a good friend of mine, and we were discussing her project on this Parkinson diagnosis. And we came up with a few of more analytical questions from how does this diagnosis, how well does it preserve when we store the samples, when we have different time of extraction, when we take the swab, and when it actually is sent to the UK. And also, of course, in the Dutch people, they have a completely different diet and there's much more milk and cheese. Would that reflect well, the smell and also the outcome of such a study? Well, it was shown in this paper actually that the Dutch samples, they really nicely fit in the UK sample. So it's a really uniform method of detecting. So I think that's a really positive sign on this diagnosis part. And that indeed in the Netherlands, we now aim to focus more on the diagnosis of Parkinson's disease in patients with clinical uncertain Parkinsonisms. And so that's where we want to continue on our side, and also really much on the new analytical methods to actually make all easier. Because what wasn't shown by Monty is actually all the work, and that actually mainly was done in the Manchester side by Ali, how much work it takes to actually get from the swab that was taken at the patient actually to get everything to the hospitals, but to actually really from Well, we have our sample kit to what it needs to actually extract and how many liters of solvents it takes to actually extract all the molecules from the swabs. So you start with your simple swab. Then you have to find the solvent that actually extracts all the molecules that you're interested in. And depending on the solvent, you actually get different type of molecules extracted. So that's already an important step. So you add the solvent, then you of course need to extract it from the swab. So there was a lot of sonication, there was a lot of recovery of the solvent, and then extraction, filtering. So there were many steps, again, extraction after filtering. Then we tried to dry it. Well, we dried it and then dissolved it again to actually have the ideal concentrations for our experiment. And then we could send this for example, to our mass spectrometry experiment that Monty already nicely explained for us today, both the GC as the LC, and this is, of course, when it's in solvent, is mainly in the liquid phase. So there we see many, many different steps that are already needed to actually do this kind of work. So what we are trying to do, and also in collaboration with Perdita Barron in Manchester, actually advancing our methods. So can we do it simpler? So one of the things is that we sometimes move now from the swab already to the cut and stick, because then we just have a smaller surface to extract our molecules from. Then maybe directly, so skip all the preparation states and maybe, for example, use paper spray. So we take the cut and stick, transfer it to paper, and then from the paper directly bring it into the mass spectrometer. And that's the mass spectrometer we need to then identify our molecules. And that works very well, but the drawback of paper spray is that, well, you miss a step. So with the GC and with the LC, as Monty explained, you actually separate different molecules as the different runners in Monty's example. So that means that you actually have to build this in again in your experiment. And that is what we do here at the VU, is we actually build this experiment that we can simplify, keep the collection very simple, keep the work after collection very simple, and then have its, let the instrument do the work for us rather than ourselves. And well, this is the picture of the lab. And so what I want to show is what kind of mass spectrometry techniques do we use, and how do we choose what we want to do. And I will show it on the work that we mainly do here in the lab, is understanding molecular mechanism of aggregation, which allows us to also control and direct this process. So here you see very simplified the molecular mechanism, how we picture this. So we start with, for Parkinson's, we have the protein alpha-synuclein, and a lot of is studied on the protein itself. And after, if you wait long enough, you have these aggregates, these fibrils, the plaques that are formed in the brain after many, many, many years. In the lab, luckily, it's a bit shorter. But what's really interesting is what is the mechanism that actually leads from the starting point to the end point. So what is there in between? And this is especially interesting as actually this intermediate, that's the protein, so the aggregation, when it just starts, it's still soluble, so you don't have the fibrils and plaques yet, but they actually are found to be actually very toxic. So can we now understand the mechanism and understand the structure and the behavior of this intermediate species and learn and use that to slow down or stop the aggregation process? Well, this is a very simplified picture, but there are many reactions starting at different time points. There are many different structures at the same time present. And then, of course, many different shapes, the interaction. So you actually need something to simplify this process. So the challenge is, how can we see this kind of structures when we have so much heterogeneity and complexity? Well, this feels like finding a needle in the haystack to find this right structure, to pick it out and study this. Or how I would always say, so to actually find Wally, because I don't know if you remember, but when I was a child, I have these books where you could had to look for Wally. within this very crowded environment. And what we then do is now find a mass spectrometry-based method, so based on weighing the molecules, to actually, well, first select a specific time point on the aggregation, then select a specific size of our cluster, of our aggregate, then look at the shape of it, so select to a separation by shape, so when it's aggregating, it forms this nice ladder-like structure, or when it's not aggregating, but just forms like a ball, so we can separate on the shape, and then look with another method, with infrared light, look at actually the real structure that is formed. So really try to disentangle the whole process. And then you get where you have this easy solution where you can directly see what you're aiming for. So this is what we're now building in our lab. And I would like to show you briefly the techniques that we are using, and maybe you can think about how they might be of interest for you. So the first thing is that we want to have our reactions in a confined environment, so inside a small droplet, so that we can control the aggregation, and so to control how the proteins are aggregating, but also to control which time point we are looking at. And for there, besides not using standard mass spectrometry, but we actually make the molecules go inside the spectrometer in droplets, as you see over here, where we form small droplets with our protein or peptide in it in an oil-like environment, and that we then bring into the mass spectrometer. Then what we then see is, well, we see every peak is the arrival of one droplet, and from this droplet we can then determine the content of this droplet. And that would look like this. So here we have a mass spectrum. So on this axis we have the mass over charge, and here we have the intensity. And here we see, well, the peptide we put in to test this when we use the normal mass spectrometry. And here, when we actually average over the same time of droplets. So you see, it doesn't really matter if you put it in a droplet or with normal techniques of the instrument, we can see the content. If we would now sit in between droplets, of course, then we see nothing. And if we would now pick one droplet, so we can really see the content of one droplet at a time. And of course, the signal to noise is a bit lower because we have only one droplet, because we can really see the content of one droplet each time by weighing its mass and see what is in there. And that we can then use to study the aggregation. Well, remember we had this extensive solvent, this extensive preparation from the swab to all the steps to take the molecules from the swab and bring it into the mass spectrometer. And if you would replace this by, for example, this paper spray option, what you would have then is that, well, we've missed this separation on forehand, this gas phase chromatography of liquid phase chromatography, like Monty explained, is not there anymore. So we need to build this separation again inside the mass spectrometer. Well, these are nice instruments that you can buy and modify. And so what we do is indeed use everything inside the mass spectrometer. So do this mass selection, then do the selection by ion mobility, by shape. And well, this works as follows. So you have your protein inside like a wind tunnel. This is how you can see it. So it's a tunnel where a lot of gas molecules are flowing. And then if your molecule comes there and it's pushed by an electric field, then when, well, it collides with the molecules, the gas molecules that are blown in this tunnel. And well, for a small folded protein, you have a certain time it comes out of this tunnel. If you would now have an unfolded protein, then of course it's big, and now it tries to move through this wind tunnel and get a lot of collision, a lot of interactions with the solvent. It moves very slowly to the channel, so it arrives much later. If we now have such a protein aggregate, then what happens is that, well, it's compact because, well, it has a lot of, the structure is compact, and typically it's highly charged. So although it's a bit bigger, because of the charges, the electric field is actually pushing it through. It just gets like a big push to get through, and it arrives earlier. So in this way, we can bring back the separation techniques that we had with the gas phase chromatography. We can bring back inside the mass spectrometer, which allow you to actually keep this process very simple. And that's what we actually did by studying well, the first steps of aggregation using Parkinson's disease. And here we looked at alpha-synuclein, and we looked at a specific small part of alpha-synuclein, which is the neck core. And this is really the core that actually, when you see these nice pictures with the aggregates, it actually is the part that is aggregating. And for today, I will show you the aggregation of the neck core, because it's slightly easier to see the spectra. So what we do is, well, we start our reaction, we bring in this peptide, put it in a buffer. We use some chemical to actually deaggregate everything, so to actually really can start. So this is our T0. Then we wait and we take a second time point where we do this experiment where we measure the mass and the shape, and we do a later time point and a later time point. So what does this look like? So what you can see is you can see a peak. And if you wait a little bit longer, you see other peaks coming up. So meaning that besides we still have our monomer, we still see now the start of aggregation. So we have 3 structures, 3 of these proteins stacked together. We got 6 proteins stacked together. And we see more and more if you would wait longer and longer. So this is the technique that we now use to follow this aggregation. Then we can combine it even with more methods if you want to not know only like what is formed, but also what is this exact structure. We can use a technique which called infrared spectroscopy. And here we excite a molecule with infrared light inside the mass spectrometer. The molecule starts to vibrate. And at one point, it absorbs more and more light. At one point, it starts to break. So with the mass spectrometer, we can now nicely measure both the original mass and, of course, the mass of the fragments that are formed. And that we can also do for alpha-synuclein or the Parkinson's peptides. And we get a nice fingerprint of the structure. And well, what typically does with infrared, what is important to know is, well, it brings a fingerprint of the molecule. And if you, for example, use it for the Parkinson's disease diagnostics, then every molecule that it was found, for example, the 10 molecules, the 4 molecules that Monty showed, they each have a unique infrared signature. So we can actually use this as an extra characterization step to see if this molecule is there and probe its presence. So this is, well, the lab a year ago when I started here. And of course, what happens, we start building, so more and more equipment is moving in. We are actually developing the instrumentation ourselves, also together with the company here in the Netherlands, MS Vision. So what is slightly different maybe from the experiment that you're used to. So we really are hands-on modifying equipment to actually make it do what we think it does best or is most useful to. So now we are developing this instrument and actually developing the spectroscopy step so that we can also have this unique diagnostic infrared characterization. So this is where we are at the moment. And this time we will use both for understanding the molecular mechanism, but also on the Parkinson's diagnostics. Well, to end, I would like to, so I've discussed a little bit on the diagnosis, I've discussed a bit on the mechanism. I would like to finalize with, well, how we want to control and slow down aggregation. And for this, we have a collaboration with Menta Use, also here in VU Amsterdam at Environmental and Health. And she uses C. elegans, so small nemotype worms. So they are like smaller than a millimeter in size. And we do both experiments in the MS, in the mass spectrometer, but we also do them in vitro or in Vermo to see if we can understand and test small molecule inhibitors in this way. Well, if we look at Parkinson's disease, we can look at, well, the symptoms of Parkinson's. So that's the mobility, the body bending. We looked at lifespan, and we looked at the formation of the plaques in the brain of the C. elegans. And the C. elegans, they have alpha-synuclein overexpressed, so they actually have extra amount of human alpha-synuclein in there, and we can see what it does to them compared to the one that don't have this alpha-synuclein. So if we look at the wild type, this is how it normally moves around on his gel. And if you see the Parkinson's, we can really see, and this is a 1 week old worm, and they typically have a lifespan of 3 weeks, but 1 week after being an adult, after becoming an adult, so that's we can see that its mobility is largely decreased. And if we would look at, well, this is the young adult worm, you see that the fluorescence, so it's stacked with the fluorescence probe, you can see that the alpha-synuclein is nicely distributed all over the head of the worm. But if we are looking at the 1 week and 2 week old worms, we see this formation of these dots, meaning that you have this formation of amyloids in the brain of the worm. Then we tested these 2 molecules. So one levodopa, of course, is very known for used drug for symptom relief. And there is Ambrexol that we wanted to test if it can have any effects on plaques. So for symptom relief, we actually looked at the mobility. So you see here, you have the number of body bends of a healthy worm. Then compare it to the one that has Parkinson's disease. So you see a decrease in mobility. But if we now start treating it with levodopa from the L4 stage, so from the young adult stage, you could see its mobility is coming back, but it was not observed for Ambrexol. If we then look at the effect on plaques, we could see, well, this is the control, so the one that has Parkinson's disease. When we add levodopa, nothing really happens to the plaques, but with Ambrexol, you see that actually the plaques are removed. So that is actually going very interesting. So indeed, you see plaque reduction. And the next step we want to do is actually take the proteins out of the worms, separate the alpha-synuclein protein and protein aggregates from the rest, and then use the mass spectrometry techniques that I just explained to you to see what happens, what the structure looks like, and to see if we can find a way to probe also these small molecules on them. And this will bring me to the summary. So in our group, we heavily developed new methods that we can actually apply to both understanding and aiding on the Parkinson's diagnosis section, but also try to understand the aggregation mechanism and see how we can actually slow down or stop this process. And this brings me to the acknowledgments. This is the group at the Biomedical Chemistry division. And the work I showed was mainly from Julia, Agathe, and Sjors, and Raya and Christina. They start the work on the worms in collaboration with Samantha. Of course, a lot of collaborations outside the university. And I would like to also introduce Melissa. She's a new tenure track assistant professor starting in our group. And she works on brain type glycosylation modification. So to see how modifications in the protein actually affect, for example, the aggregation or the disease. And she looks at these modifications from spinal fluid. So I want to just mention that she started here recently, and she would be very good to also have in our network. And then with that, I would like to thank you for listening, and I'm looking forward to this to some discussion.
Okay, thank you, Anouk, for this very interesting and nice talk. And you brought us really into the depth of mass spectrometry. But I think for most of us, it was really clear to in which direction you want to go with your studies. So I'm not sure if Rob is also wants to join the discussion. Otherwise, I can start off with a couple of questions. And also that also brings one earlier question from the earlier talk from Bert at Heart. So you mentioned you want to implement your technique for diagnostics on swabs, and also on the last slide you also mentioned the CSF. Do you also think about other samples, for instance, urine or blood?
Yes. Yeah. So well, for this particular study on Parkinson's, of course, it was, well, as Monty also explained, it was found, well, it started with the smell, and then of course from the skin and etc. And then, well, inside urine would be slightly different to study that. So the nice thing with the Sebum is that it's very simple. You can just easily collect it. It's non-invasive. You can do it everywhere. So was the nice way to actually start from that's why we started with the swabs. But then of course the sample preparation side, that's of course always that's not shown typically, is kind of intensive, and it costs indeed like hundreds of liters of solvents. That is also not shown here. So that's why we started to actually make it simpler. But this technique, so for example, to find biomarkers or help to diagnose with many diseases, it has been done using blood samples or being urine. And so the novelty here is actually this also the type of the type of biomaterial, so to say, and it's so easy to collect.
And then maybe related to the sample preparation, is also a question posed by Misha Wilhelmus. So I understand you also use HFIP, hexafluoroisopropanol, if I'm correct.
Yes.
And that disrupts, of course, the multimers or the aggregates. Do you still expect to see then difference, or I think I can also understand that you lose some information when you disrupt the aggregate?
So we do it both with and without the addition. So actually, we wanted to actually control the start. They are when we really want to study the aggregation from T = 0. We actually want to disrupt everything and then let it aggregate in solution. With the worms, of course, or when we extract it, we don't want to do that, because actually then we want to keep them intact. But typically it's a trick that we use sometimes to actually have a T0 to actually learn a bit about the kinetics that's going on and how fast. For example, if you do a mutation in the protein, if it will change the formation of aggregates, the kinetics of it. So if the mutation speed things up, slow things down. So it's a trick, but we typically do it with and without to actually monitor the effects. What we have been adding.
Okay, great, thanks. I'm not sure. Maybe it's also good to get Monty back in view, but maybe.
Yeah, I'm back.
Hi, yeah. Or maybe
I can stop sharing also.
Stop sharing, yeah. Then we can see each other. And so for Anouk, are there also another couple of questions in the Q&A for you, but because of the time, and I think it would be nice to address a couple of more common questions to you. So the other questions we will send to you afterwards. And I think a nice, more general question, which was also posted in the Q&A earlier. Do you also think about not only diagnosing in Parkinson's disease, but maybe also other neurodegenerative diseases, or for instance, could you use swabs also for Alzheimer's disease, or even maybe other alpha-synucleinopathies like dementia with Lewy bodies? Or what are your ideas about that?
Well, we have collected samples from atypical Parkinsonian disorder, so PSP and MSA. They are being analyzed at the moment, I think, to see whether we can distinguish between Parkinson's and conditions that look like Parkinson's. We haven't looked at other neurodegenerative disorders as yet, like Alzheimer's or motor neuron disease, but there's certainly some discussions about maybe doing that.
Yeah, so it's like, but maybe it was not, well, it was shown, indeed also with Monty mentioned it, that it started as a small study because of this connection with Joy. But it's also a very time-consuming study. I mean, from the moment it started to now. So I think now we have the workflow a bit better under control, but it's indeed, it would be nice to actually expand, well, the research groups or the people that work on it, because then we can actually do many more samples and screen them. And it's hugely time consuming on the analytical side. So that's why indeed, well, for example, I joined the team and more people joined the team to actually have more methods. But that's why we also actually still developing the method to actually have it more easy and to actually find other ways to actually be able to screen more diseases. And well, there are, for example, other diseases known that have also a particular smells, like Monty already mentioned, 2 of them, but there are many of them. And well, if they have a smell, there must be a molecule responsible for the smell, so you can measure it. It's just,
yeah.
It's just little simple things, like we started the whole study using gauze swab, which just seemed the obvious thing to use, but we didn't imagine when you get the swab in the lab, you got to, of course, get the solvent and add it to the swab, and these swabs are quite big, so we're going through liters and liters of solvent, and so now we use Q-tips. Just a simple, the little Q-tip things with little cotton buds on the end. Just a tiny little change like that has made everything so much easier. So these are the things that we've been learning on the fly, if you like.
Yeah.
And maybe it's something that maybe also Rob can comment on. Are you also doing prospective studies? I think because, for instance, using the swabs, I mean, it's not a non-invasive technique, and maybe easy to collect in clinical trials. Are there also ideas of doing this prospectively, and just in the end that you can select the most precious samples that you can eventually also validate your technique with? So if a patient already is in an early stage of a dementia or a neurodegenerative disease, that you in the end can follow the patient, but that you then have the earlier swabs to just to see if there are already changes in earlier stages of the disease. Is this also ongoing already?
So Anouk and I tried to get funding for a study where we compare the swab technique, so to speak, the Sebum, with other techniques like that SPECT scan, for example. And what you're asking of is more, for example, disease progression. And I think Monty knows more about this, because then you need to sample people in different stages of their disease. And you could also, maybe if you have a disease modifying agent, would also change what you see in the swab. But I think that's has to be investigated. We are starting here with the ProPark study, for example. It would be nice to have the patients swabbed as well, if you have a large cohort of patients. But I think surely that's very interesting. Okay, can I ask a question myself, or is that allowed?
Yeah, sure.
So I learned a new concept, that was the in-worm test. And I was intrigued by the fact that that the worms they overexpress alpha-synuclein, and that they respond to levodopa, which is something nice I was quite amazed of, that happens. Yeah. But then with the Ambraxol, you can remove the alpha-synuclein, and that doesn't change anything.
No, that's indeed a very good observation. It's even worse. The Ambraxol, well, actually the solvent that came with the Ambraxol actually killed the worm a little bit. Not a little bit, I mean, that's not possible, but actually reduced the lifetime.
Okay.
So that's something that we're still investigating. So this was just a first test. Can we use this? But then it works very well. Screening looks very simple, and well, that's actually Samantha uses very. See, now we recently also started here in Amsterdam, so that actually is great to have this connection. And now we try indeed to find a way to have this platform that we can really use it to test different small molecules. Yeah. But yeah, so amroxol is not the nicest molecule. We just yeah, but yeah. No, but for the levodopa, I mean, we really could also see when we different if you dose it on a longer time scale, it works, and yeah. So,
amazing.
Yeah. So we are curious what's happening also on the molecular level. So how does it work? So that's, of course, we just see it works. We see on the worm, and that's why we're now interested in actually extracting for example, extracting parts of the proteins in the worm to see if we can learn about what's going on. Is the levodopa binding to alpha-synuclein? Is nothing related at all, or we have no idea yet. So that's actually really work in progress.
Okay.
So.
Okay. Rob, do you have another question or point for discussion?
No.
No. Okay.
Rather in the Q&A. I mean, I can.
Yeah, I think there's an interesting one remark in the Q&A by Bram van der Graag, and he mentioned if he also can detect differences between men and women in the swabs.
I think there must be. They did some analysis to check that gender didn't affect our ability to distinguish between Parkinson's and controls. So they had gender as a kind of covariate, amongst other things like age and things like that. And so I can say that it doesn't affect our ability to distinguish between Parkinson's and control. But I don't know if they specifically looked for molecules that were different between gender.
I don't think a little bit, but the problem is, well, the cohort, of course, which has have Parkinson's is mainly male dominated. So the sample amount of the samples we had for females is rather small. But so far we did not, because I would expect, because the whole metabolism is different, that there would be different molecules. But so far, the 10 that we found were both in male and female participants. I think just this moment, just the cohort, actually the amount of women that we have is too small to actually find. So hopefully with the many centers that now are joining, we will have, well, maybe it's not nice to say, but we want, it's nice to have more female related swaps. Yeah, but then it's very interesting. To see this.
So I understand, of course, the number of samples is limited for now, but do you also expect that in the future that you have to combine forces with artificial intelligence to make distinctions between profiles?
Yeah, I think it's in what Monty showed. I mean, there's a huge amount of data analysis. So I only showed the data the separation part a little bit more, but there is a huge amount of data processing, and then yeah. So.
Yeah, it's all a little bit beyond me. Some of the statistical techniques, I in a 20-minute talk, I pulled the stats out of it. You'll be glad to. That's the bit that didn't make it. But there's all sorts of different ways they use. There's machine learning techniques. There's things like support vector machines and partial least squares, discriminant function, and that. There's all these different ways they do it. But I think in the end, the machine learning techniques have not been what they've used. It's just been standard regression, if you like.
Yeah. Okay. So I'm sorry. I really like the discussion, and I think for me, but I think also for other people, I think these were two very inspiring presentations, and then also studies that you were doing. So it opens up, I think, a lot of new methods and ideas, and also possibilities for the future of diagnosis. So with this, I want to both thank you for the presentations. And looking forward to the future results and the development of these techniques. So thank you very much.
Thank
you. I also want to thank Rob de Bie as a co-host today. And before I sign off, I want to share my screen with you and also announce that on December 16, we have our next TN2 meeting. So please register. And the next webinar will be on compulsivity, impulsivity, and attention, another Amsterdam Neuroscience research program. So hope to see you all on December 16, and thank you for your attention and have a nice day.